encoder. And the way MrT5 merges the sequence is using a delete gate and an early encoder layer. So I'm going to step through this animation real quick. I think there's some latency, so the animation is not showing up. Give it a second. I think my slides got frozen. Can I go back? Okay, I think it's going now. Okay, give it a second. I think the animation was maybe too much. Okay, it's going now. So this was supposed to be very smooth and elegant, but I think it's not smooth or elegant. So after processing through a fixed number of encoder layers, MrT5's delete gate takes in the contextual hidden states for the byte sequence and outputs a sequence of numbers that tells you which tokens can be deleted from the sequence and which can be retained to be processed by future encoder layers. So in the example on the slide, it's kind of the main idea is that can we leverage the information redundancy that we have when we are processing raw bytes or characters? So maybe through the contextual representations that you derive from the attention mechanism from a few layers, the model can figure out that it's dealing with the word the, and maybe this H is not so important for future layers. And the delete gate learns this implicitly, what information you can prune because it's already contained in other tokens via the attention. So during training, MrT5 uses soft deletion via soft attention masking. The deleted tokens are masked out from the attention mechanism of future encoder layers and cross attentions. And during testing, MrT5 uses hard deletion via hard column removal, which results in the inference runtime speedup because the majority of the transformer stack is operating on a reduced sequence length. So what exactly is this gating mechanism? We'll take a closer look at the actual math, and I'll step through each part individually. So first, this H sub L represents the hidden states output by the layer where the delete gate is placed. So this is in the MrT5 encoder. And yes, so L represents what layer of the encoder we're dealing with. And these hidden states are then passed in through a layer norm. This is just a detail because we're dealing with T5, we use RMS norm. And next, the normalized hidden states are multiplied by this weight matrix. So this is like basically a linear layer and adding a bias term. And the vector of ones is just for broadcasting across the sequence length dimension. Finally, the logits are input to a sigmoid function, which we then rescale by a large negative constant. And the reason we do this rescaling is that this basically shapes the sigmoid to now be between 0 and k, which is this negative constant. And this is how we achieve the deletion functionality because it basically acts as a soft attention mask by having this large negative value that weights down the softmax. And finally, I wanted to note that the gate only adds an additional 2 times the model dimensionality plus 1 parameters. So this is very parameter efficient. And if people have questions about where these numbers are derived, I'd be happy to answer them. Now I'll go into a little bit more detail about how the deletion mechanism works in training versus testing. So during training, when we do soft deletion, the outputs of the delete gate are used as an attention mask for subsequent encoder layers. So just to be more clear about this masking process that I talked about previously, the gate values that are output by the delete gate are added to the attention scores. And again, we broadcast across the sequence dimension. But basically what happens is that any tokens with gate values close to 0 will not be masked out because it will basically be unaltered that input to the softmax will be unaltered. But any gate values close to k, since k is a large negative constant, will be masked out. And during inference, to achieve runtime speedups, we do hard deletion, where a threshold is applied based on the delete gate's output values. Here we have, if we want tokens with gate values close to 0 to be kept, they'll not be removed when we use k/2 as a threshold, which is just the middle value in between 0 and k. So the gate values close to 0 will be kept, and the gate values close to k will be removed. And this creates the effect of actually having inference runtime speedups. Just another detail, we can adjust how much MrT5 reduces the sequence, and we do this using a tunable regularizer loss that encourages the gate values to be more negative. So these are just the average of the gate output values, and this is added to the model's cross entropy loss. So if the gate values are more negative, you're going to get more deletion. And this alpha hyperparameter allows us to vary the weighting of this loss term, and we can actually tune the models to have more or less deletion. The loss as it's currently formulated as this slide can nudge the model to have more or less deletion. But if you want to target a specific ratio of deleted tokens, let's say I want 50% of the sequence to be reduced in order to target a specific amount of runtime speedup, we actually have an algorithm that can target a specific ratio of deleted tokens. And this is using a controller algorithm that I don't have the time to go over in the span of this talk, but I would also be happy to answer questions about that. Yes, whenever I refer to a PI controller, it is referring to this algorithm that allows us to have a specific percentage of tokens removed. Are there any questions so far? I should have said I'm happy to take questions throughout the talk. If not, I can keep going along.
I have a question.
Yes. Yeah.
So in the inference, since is it autoregressive? It's autoregressive, right?
Actually, this is not autoregressive. So this method works on encoder models.
I see. I was just wondering that as you predict more tokens in your inference, let's say if you just have T and H in the prediction, maybe H is required, but as soon as you predict E, you want H to be deleted. So does that happen in decoding?
Yeah, so I'm currently thinking of follow-ups to make this method work for in an autoregressive setting, and that's exactly like the problem that we would face, that you don't know. Right, but also you just don't know what the whole, you don't know what the future is going to bring. Maybe something will be, maybe something early will be useful when, for predicting something in the future, but you just don't know, right?
So right now, is everything predicted at once?
Yeah, so these are this is in encoders only. This method works, yeah. So it could work on, it actually doesn't just have to be T5 models, but it could be any encoder model that you could apply this to, like a BERT model, BERT-based model. Yeah. All right. So I'll go on to the first set of experiments. And in order to just get a sense of the sorts of deletion patterns that MrT5 learns, we first train tiny 15 million parameter MrT5 and T5 models on from scratch on 3 diagnostic tasks. And the purpose of these experiments is just to understand whether MrT5 merely learns to drop tokens when they're irrelevant to the output, or if it actually effectively merges relevant context into a shorter sequence. The first task is a simple vowel removal task where the model must take in a sequence of random consonants and vowels and reproduce the sequence with all the vowels removed. And this merely asks whether MrT5 is dropping the tokens that are irrelevant. The second task is a contextual vowel removal task where the model must delete vowels that are followed, if only if they are followed by a lowercase consonant. And here, this is again merely testing dropping tokens that are relevant, but it's conditioned on surrounding context. And finally, the sequence merge task requires the model to copy sequences of consecutive ABC units into one character, which is basically translating ABC into D. And this will ask whether MrT5 learns that these tokens represent a unit and can leverage that in a way to increase the amount of deleted tokens. And here, we just train MrT5 models with a constant alpha parameter that adjusts the deletion rate. So here we just kind of let it delete and see what happens rather than telling it we want a specific percentage of deletion. And for each task, MrT5 is capable of learning to drop the tokens that are particular to the task or relevant to the task. So for example, for the simple vowel removal task, MrT5 learns to drop exactly the vowels in its deletion mechanism. For the contextual vowel removal task, it can learn to drop exactly the vowels that follow the lowercase consonants, which are the exact vowels it's supposed to drop for the task. For the merge task, it also learns to drop the characters if they fall within these ABC sequences. So what this is showing is that, and for each of these tasks, MrT5's accuracy can nearly match the T5 accuracy while reducing the sequence length. So this shows that MrT5 is learning deletion patterns that are particularly relevant to the task that it's supposed to perform.
So the sequence length is the context input length, right?
Yes.
During the generation, the sequence length is you still have to generate one character and then.
So in the encoder decoder model, right, these sequence lengths that I'm talking about are the inputs to the encoder.
Exactly. So yeah. When you're generating, you still generate one character. Right?
Yes. So
these reductions are in the context, whatever goes into the context of the input.
Right. So yeah, that's a good question. So these reductions are based on what goes into the encoder. When I report runtimes in the paper, that includes both the encoder and the decoder's processing time, because that's going to be relevant for the whole thing. Yeah, so any runtimes that are reported include the time it would take to also go through the decoder, which is not affected by our architecture. Yes, so this sequence length reduction is just so it's based on the input to the encoder. So yes, so if the encoder's input was 5 tokens long and it deleted 1 token, then that would be a 20% reduction. Yeah.
But then your reduction is happening during the encoder phase itself, like you have softmax, which is dropping your elements with the attention mask. So in general, you're giving the same input size, which was originally given to the encoder.
Right. So during training, the deletion is implemented as masking. During inference, where you would actually want to have the faster runtime, or I would make the argument that it's more important to have faster inference or test time improvements in runtime. The tokens are actually removed from the sequence length.
Like during the tokenization phase itself. Right?
Like after a couple of transformer layers, so I could be more specific for each experiment, but after just a couple of the encoder layers, the sequence is reduced based on what the gate tells us.
So
they're in the middle of
like
the encoder.
Take the attention mask after the training and just use it for the tokens at the input phase itself. Because even if it's going for like 3 or 4 layers during the inference, you still are giving like the same input length to the input.
Sure. Our argument is that if you put it at a low enough encoder layer, then processing the whole sequence on just a couple of layers is marginal,
quite less
compared to the whole stack. Yeah. That's a good question. And following the simulations, we have some experiments on continued pre-training experiments. So this is on real language data, where we train MrT5 on Byte-T5's original span corruption training objective. And this is just the same method that was used for pre-training Byte-T5 and T5 models. And we train several MrT5 models this time with different sequence reduction rates using the controller algorithm that I briefly mentioned. And in our setup, we train all the training and evaluation data is sampled from multilingual C4 and covers 15 different languages. To measure performance following adjacent work in this area, we report bits per byte, which is a tokenizer independent version of Perplexity. Since we're already dealing with byte-level models, this just means multiplying the model's cross-entropy loss times a constant factor, but this is just to be consistent with adjacent work. And finally, we note that all the models are initialized from a pre-trained Byte-T5 small, which has 12 encoder layers and 4 decoder layers. And we place the delete gate at layer 3, so it's only the first few layers that process the whole sequence. And we determine this via like a hyperparameter sweep that's also included in the paper, where we wanted to place the layer as low as possible with minimal effect on performance. And we found layer 3 to be optimal for considering both trade-offs. In addition to training MrT5 models, we also have several baselines in our that we consider for comparison. So first is an unaltered Byte-T5 architecture that we just also continue pre-training on the same data. There's also a random deletion baseline where some percentage of tokens are removed from the sequence randomly. We have a fixed deletion baseline where, based on this heuristic, then maybe only parts of words are important for inferring the whole word. We delete like different percentages of the ends of words. So if you see different fixed deletion baselines, it just means a different amount of word endings were chopped off. And in addition to these baselines, we also train models that use alternative downsampling methods, recalling some of the related work that I began with in the talk. So we have a boundary predictor baseline where we basically take this module from the hourglass transformer architecture and place it at the same spot in the T5 architecture, and do continued pre-training in the same way for these architectures. And based on the hourglass transformer, you can actually have a different amount of downsampling using different prior probabilities of predicting a boundary. So these are just details of their implementation, but we adapted it to the T5 setting. And following Google's K9 model, we also have a convolutional pooling baseline, taking the method of having a 1D convolution before passing their inputs to a larger transformer. We place it again at the same spot in the T5 encoder, and we train these models the same way, kind of just continued pre-training on the same data. I'll now walk through the results of the continued pre-training experiments. On this plot, we show bits per byte on the y-axis versus the sequence length reduction on the x-axis. And I first plot Byte-T5 just in the corner because it presents the lower bound on the best possible loss you can get, and it doesn't reduce the sequence at all. So that's why it's in this corner. Next, I have the performance of several MrT5 models with different deletion rates. More deletion results in generally higher bits per byte, but MrT5 is generally competitive with Byte-T5, especially when we can compare it to other baselines. So here we have the random deletion models. Here are the fixed deletion models. The alternative pooling baselines are not that competitive with MrT5 either. And in general, we find that MrT5 has a much lower bits per byte for similar sequence length reduction rates as the other alternative baselines. And now that I've shown you that MrT5 can achieve good compression, how does this actually translate to runtime speedups? Considering yes.
Like how would this compare to just DPE tokenization?
That's a great question. So I guess on average for English, there's on average 4 or 5 bytes per token. So in order to get competitive with DPE tokenization, you have to use about this model. But still, there is an encoder portion and a decoder. The decoder portion is still, it's lightweight, but it's still operating just on the whole byte sequence. So in general, we didn't make direct comparisons to the original T5, but in order to get close enough, you would use something around the 70%. But again, considering that this is only for the encoder model, the encoder part of the model, the comparison would be a little bit difficult. I'd still say that it wouldn't be quite as fast just because the decoder is unaltered. So we're going to focus back on these 5 MrT5 models with different sequence length reduction rates. And if we compare their average inference runtimes for a single sequence, we can see that models with more deletion do result in a runtime speedup relative to Byte-T5. For example, the model in the middle that reduces by about 50% achieves a 30% runtime speedup. And in general, with more deletion, you get a faster inference runtime. Now I'm going to home in on one MrT5 model and see how this plot looks when tested on individual languages. So we had multilingual continued pre-training, but we can, with general, let's say for this model, we said we want 50% deletion on average without telling it any prior about how much it should delete for each language. And what we find is that MrT5 basically learns language-specific deletion rates implicitly. I should clarify that in this plot, Byte-T5 is included only as a comparison of bits per byte because Byte-T5 always reduces the sequence length by 0%. It doesn't reduce the sequence length at all. But what we can see is that for some languages that have more information-dense scripts, I would say Chinese on average, one character could represent a whole word, has the least sequence length reduction, whereas some languages, a lot of Latin scripts, have a lot of information redundancy. They're pushed farther to the right on this plot. At the same time, MrT5 only introduces a slight bits per byte increase compared to Byte-T5 for each language. So it learns when to delete more when it can, basically, without having a performance hit. And if we look at the loss for individual examples, so each individual examples can have different amounts of deletion. MrT5 also learns to delete tokens when it would not result in a large increase in bits per byte relative to Byte-T5. So on the left, we have the per sample increase in bits per byte versus the sequence length reduction for each of the MrT5 models that we train with different deletion rates. And on the right, we have the same plot, but for the models that are deleting randomly. And for MrT5, the correlation between the increase in bits per byte and the sequence length reduction is weak or negligible, whereas there is a moderate positive correlation for the random deletion models. So yeah, that's what, are there any questions about this plot? If not, I'll move on. Separate from the models I've talked about so far, we also trained a large Byte-T5 and a large MrT5 model. These each have 1.23 billion parameters each. Again, these are continued pre-training experiments. And we found that MrT5's efficiency gains were even greater at a larger model size, while the bits per byte comes closer to matching Byte-T5's. And this largely has to do with, we placed the gate, again, just at layer 3, but when you have an encoder that has 36 layers, only processing the whole sequence in 3 layers, and then operating on a 50% shorter sequence on 33 layers results in a much bigger gain in inference runtime. So this just means that as we scale things up, the efficiency gains could be even greater. I wanted to note that both the MrT5 small and this large MrT5 model, both with about 50% deletion rate, are available on Hugging Face if you'd like to download them. And the model card has a quick start example if you'd ever like to use these models. And with the remaining time, I thought it might be good to show some of the results we had on fine-tuning MrT5 on downstream tasks. So we first started with 2 benchmarks to assess its multilingual capabilities. The first was the XNLI corpus, so this is natural language inference. And here, the setup is we train just on English and assess how the model does zero shot on the other languages. And in our second multilingual evaluation, we did tie-dye QA. Here, given a passage that is guaranteed to contain the correct answer, the model has to generate the correct answer to the question. And here we have results for Byte-T5, MrT5, and this is the boundary predictor baseline and the convolutional pooling baseline. And in general, MrT5 outperforms the boundary predictor and convolutional pooling baselines while being a much faster model and having generally the closest performance to Byte-T5. So I've just highlighted where MrT5 is on these plots. And you can see that it gets very close to Byte-T5 on both of the tasks, or even exceeds Byte-T5 on XNLI, and while having the fastest runtime decrease, especially or when compared to the other baselines. And we also tested it on 2 tasks that require performing character level manipulations. These are taken from the character level benchmark from Huang et al. And the first is a spelling correction task, where the input sentence contains some spelling error, and the model has to reproduce the whole sentence with the error corrected. And determining the correct spelling requires that it incorporates some context from the sentence. And the second task is a word search task, where the input follows this sort of format where it will have like a kind of a scrambled sequence of characters, and it needs to locate the English word within the bunch of jumbled characters. And it has to also be related to the definition given in the prompt. There was fine tuning here, yes. And so again, these are the results. And in general, MrT5 stands out as the more efficient model. It achieves notable reductions, like 50% for the spelling correction task, about 75% reduction for the word search task, and these result in considerable runtime speedups. Generally, how much runtime speedup you get on a task depends on whether the encoder has a very long sequence length, which was why, yeah, these tasks required kind of very long sequence lengths compared to some of the other tasks in the benchmark that were like 10 characters long, which is why we tested on these specifically. And that's, I wanted to end, so yeah, these are the bulk of the experiments. I wanted to end with some future directions that we could take, building on the work that we started with MrT5. So first is that this deletion gating mechanism could be applied to any encoder model. So you could just make a faster character or subword BERT and maybe you could call it Mr. Bert. Um, and yes, this method, we're currently thinking about ways that it could be adapted to decoder models. And that's something that we're working on actively. And I think it's worth mentioning other recent work. This model is from Meta. It's called the Byte-latent transformer. It came out last December. And here they scaled up byte-level models to 8 billion parameters. And it would be great to see if alternative architectures like MrT5 would scale up, or how they could be even better if we could scale them up or train from scratch. Especially like, for instance, a method similar to MrT5 could be put somewhere in the local encoder part of the byte-latent transformer. Yes, so here we introduce MrT5, a more efficient variant of Byte-T5 that uses a learned token deletion mechanism to dynamically reduce a sequence in its encoder. And in general, MrT5 moves us closer to byte-level, making byte-level modeling more practical and possibly eliminating subword tokenization, which is the last piece of the classical NLP pipeline that's still present in large language models. Yeah, thanks so much for having me. There's a QR code here for the paper. And yeah.
So what stops you in principle from just directly applying this to decoder or autoregressive models?
Yeah, so in principle, we could apply this directly. So here, let me, actually, I don't think I need to refer to a particular slide. I think that the major challenges come with kind of making this significantly different from what's already being done with early exit models in a decoder setting. So early exit models kind of put decide to do the token prediction at some intermediate layer, like the next token prediction in a decoder at an intermediate layer. Whereas what we want is kind of, we don't want next tokens to have to attend to these deleted tokens. And I think we could incorporate that aspect of MrT5 to make it more efficient than what early exit models are doing. But yeah.
Is it that the training still works, but this is something that doesn't make it direct? It's like for training, like I can imagine, like, so basically the delete gate predicts an intention mask.
Yeah.
The only difference is now you need to overlay a causal mask, but I feel like the learning would be the same.
I think training would be pretty straightforward.
Yeah.
But when you're predicting one token at a time, I think it's kind of, it becomes less clear, right?
So there's some issue with like KV caching.
I think there will be issues with KV caching. Also, to full disclosure, I haven't started implementing this yet, so we'll see if there are even more challenges. But yeah, it's kind of like you have to predict the next token at some intermediate layer, and then also enforce that like following tokens don't attend back. That's kind of the main idea that I've been thinking about that would make it novel and different from other architectures for decoders. Yeah, but I think that some implementation details I do see as being pretty different. Yeah.
Can you explain the intuition that this, like, I guess, how's like the analogy to early exit?
Yeah.
So that this would essentially be early exit.
I don't think this would be essentially early exiting because I don't think that this version is essentially early exiting, but in a decoder model where when I think of early exit being applied to a decoder model, it's kind of like the classification is made at an intermediate layer. But so you kind of get speed just by skipping later layers there. What we would want to do to make that would be more akin to the method that we applied to encoders is not allow future tokens to even attend back to things that are deemed unimportant, which would be closer to the idea that we have here.
Right, so in an encoder only model, the way that you would say, like mask out a token, it would be that, I guess, at a particular token, you would say, oh, I'm not gonna go forward before looking at the next token, that's what you, okay, I think.
So something like that, yeah.
Yeah. Which would be inherently quite difficult, because without, let's say, the or whatever, like realizing that you don't wanna go forward with H without having to see E afterwards.
Yeah.
Okay.
Right. So this kind of made a ton of intuitive sense when the encoder gets the whole sequence at once at the input. And yeah, I think it makes a little bit less intuitive sense in a decoder. But we're still thinking, just in the thinking stages about how we would do this. But, yeah.
Curious about the deletion events you will be particularly if you mark some element.
Oh yeah. That's a great question. So since we are applying this to T5 models, the way T5 encodes positions is using these learned position biases. So it's just a bias term that's learned for every position in the sequence. And they kind of fall into buckets such that as you get farther away from the current token that is attending to the other tokens, the positions of the others will just all pool to the same bias term. So that this was just a particular way they decided to implement positions. And I only think T5 did it this way. But after the deletion is performed, or we also have to perform deletion on the stored position biases. So basically, if a token was at position 3, its bias will stay as the position 3 bias term. It's not like we don't kind of reset what positions there are after the deletion. Yes, so in the example from the diagram, so it's still T and E will be using the first and the third bias terms from layer 3 onward. Yes.
Just help me think through this for a second and then tell me whether I'm getting this right. So I really liked your motivating example of the strawberry.
Yeah.
I think it's a very intriguing one because usually it's not a relevant thing that we talk about, how many R's there are in a strawberry.
Yeah.
But so it seems part of the motivation would be that based on an instruction that you give, the model would have the general capability of paying attention to specific characters in the string and then flexibly adjust to count the number of R's, count the number of A's, count the number of T's, etc. Which I thought was really neat. What I was hoping I would also see some evidence for is that you can actually do that without fine-tuning and introduce that flexibility through instructions.
Yeah.
I'm curious to see, obviously, like the H and the is something that's very easily, that can basically be deleted all the time. But will it be able to have that flexibility that when I say count the number of H's in the sentence, that it will actually not delete that H anymore, even if you don't fine-tune for that specific task. So am I getting this right? Do you feel like you have evidence for that?
Right. Yeah. So yeah, I didn't do much few shot prompting experiments also because I mostly was working with Byte-T5 small, which I just don't think at 300 million parameters, the capabilities are limited. And I should maybe experiment more with the slightly larger 1 billion parameter models that we train. But in general, I just don't think the prompting capabilities are quite great at those scales, and that is also why I want to scale it up and see what capabilities would emerge at the scales that most people are thinking of when they're thinking of just giving an instruction to a language model and seeing how it does. But yeah, I think you're right on point about ideally, regardless of the fine tuning, you would just want to see it dynamically keep or remove information on a particular instance level, which we kind of got at with some of the experiments looking at per example losses, but yeah, I'd love to do this more deeply on like specific types of data, what different deletion patterns show up. But
Yeah,
yeah.
I'm wondering if like on this an experiment where you don't need a prompt, maybe you know, just keep have basically a test set that is very exclusive, that something that through the task that you fine-tune it on, it would never learn to delete a specific character, but that's exactly the character that you trained on, that you test on.
Yeah.
Whether that's then sufficient to override it.
Yeah, I think that's a great point. Yeah, and more follow-ups, I would want to look specifically, or like, I guess have more of the controlled kind of experiments I had with the simulations. The simulations were maybe trying to get at this. But I think this could be done with many different types of data sets, and even like different, looking more closely at like what happens in different languages too. Yeah, that's a great question.
I have a question.
Yeah.
Could you go back to the slide where you talked about layer 3 is the optimal layer?
Sure, yeah.
How did you?
Yes, so I don't actually have it on the slides, or do I? Wait, I do. I have it in, I have it in this appendix. Yeah, so basically what we did was train several models that have the delete gate at different layers at the same time targeting 50% deletion. So all of these models delete about 50%, but it's just at what point do you start deleting? And we basically chose layer 3 because it had the like lowest bits per byte, so it's pretty good here. Like layer 5 gets even lower, but we're like, we can do pretty well with layer 3 while yeah, we can have pretty decent performance in layer 3 while having it as low as possible. Whereas for layer 1 and 2, the loss was just too high.
And do you expect this to be like a fixed number or dependent actually on the layer, not total number of layers?
That's a great question. I think ideally you would maybe want to do a sweep in any new model, but we actually just applied layer 3 to the large Byte-T5 without doing this sweep because we couldn't afford to do the sweep on the 1.5 billion parameter model, or I guess I didn't have the time to do it. And it works pretty well at layer.
So the table usually is based on one size of the.
Yeah, this is based on the small model, the 300 million parameter model. Which actually the 300 million parameter Byte-T5 is actually, it's still quite a big model because there's only 256 embeddings for the 256 bytes. Whereas when I think about like 120 million parameter GPT-2 is actually, I think, closer to 40 million parameters are for the embedding matrix or so. Yeah, so those 300 million parameters are really like in the model itself.
Let's go through the talk.